Today we're going to delve a bit more into black holes. So although we're still going to be quite mathematical for some of the lecture, we're leaving this sort of geometric type of notation behind for a moment. So it's got a chance to kind of seep down into your subconscious, and hopefully, you know, next time you meet all these labels, indices, you know, on geometric things, hopefully they'll cause less concern. So yesterday we used Cartan to find the curvature of a spherically symmetric space-time and found solutions, which you were familiar with, which was the Schwarzschild black hole, and also I talked about the cosmological constant and the de Sitter space in the static coordinates. So today I want to delve a bit more into those black hole solutions and talk about causal structure, because that's really what is the sort of defining feature of a black hole. The defining feature of a black hole is it's black. And why is it black? It's black because light can't escape. And from relativity, if light can't get out, nothing can. And so in some sense, that's a causal barrier. If we can't see behind it, it's like an, you know, in some intuitive sense, an edge to the space-time. So I want to explore this a bit more. I know you've sort of seen analytic continuation behind event horizons, so we'll do this again in the Schwarzschild case, and construct a coordinate system that completely covers the full Schwarzschild geometry. So we're going to maximally extend the Schwarzschild space-time, and then we'll describe a way of encoding the causal structure very concisely and visually in Penrose diagrams. So we'll go through it once in gory detail, sort of explicitly sort of compactifying space onto a blackboard. But then I'll sort of say how, in reality, when we are faced with a geometry, we tend to just not bother with all these steps and just identify the key features of it. So I've put down sort of as our starting point the Schwarzschild metric, and just for compactness, rather than writing 2gm each time for that coordinate singularity of the metric, I'm just going to write r+, just to sort of say, well, that's where these coordinates break down. So the Kruskal coordinates are the coordinates that extend across the event horizon. So we need to construct them, and this is a sort of two-step process. We first start off by defining what's called the tortoise coordinate, which we write as r star. So given that we're thinking about boundaries of where light can and cannot go, it would be helpful if the first sort of starting point of our metric actually had a sort of radial coordinate, so that, you know, the t equals r or t equals minus r are null geodesics. So if we define our r star as the integral of 1 over 1 minus 2gm on r, pluses there, then this part of the metric here becomes the same factor as sort of GTT times dr star squared. So our null geodesics are now our radial geodesics are now t is plus or minus r star plus a constant. So now that means we can think about building a coordinate system that is based on these null coordinates, and then the idea is that we can follow that through the event horizon. So our cruscals do precisely that. They use this t plus or minus r star, so those are the sort of null directions, and then because we've still got this sort of 1 minus 2 gm on r sitting in front of dt squared minus dr star squared, that sort of gives a logarithmic singularity of the coordinates. So we exponentiate to go beyond that. So let's see that. So in null coordinates, usually the metric is like du dv. So let's have a look at what du dv looks like. So in each case, when we take du or dv, we simply take the exponential there so that's our u and v. We've got two r pluses, so we've got an r plus squared out front, and then we have to take the derivative of the argument of the exponential. So in each case here, we get a dt plus dr star from v and a dt minus dr star from u. And then that's over 4r plus squared. So that's just looking at what du dv is.
Sorry, in the signs and the exponential, so in u you have minus d plus r.
Yeah, sorry. That's right, it's a minus sign. I would have realized I'd made the sign error when I got to the next step.
On the other.
Are we good now? No?
It should be on the other term in the exponential, right? Yeah.
What have I done?
The one that has the minus on the minus r star should have the minus in front of it.
Oh, right.
The overall minus.
Thank you. Too many minus signs. Just imagine if I changed my signature as well. That would have been a disaster. It's the classic minus signs, factors of 2. Just accept it. You're going to make those mistakes. Right. So now are we good? I think we're good now. Yes? Good. So it would have been obvious by the next line once I tried to put things together that I'd messed up. So, but thanks for stopping me before I got there. Right. So where are we? Okay. Next line is a quarter. E to the r star on r plus, and then dt squared minus dr squared over 1 minus r plus on r squared. So that's just replacing dr star squared and tidying up the exponential. So now, if I look at what r star is, this is e to the r over r plus. That's the first term. And then the second term is 1 minus r plus n r. Just looking at the definition of r star. So what I see is that du dv is up to a regular factor, this exponential of r and r plus, is actually the first bit of our Schwarzschild metric. So we've now managed to construct a new coordinate system, capital U and capital V, that has no problem at r equals r plus. So our full metric is what I've written at the bottom there. So this is our full metric. And it has no problem at r equals r plus. So obviously, I'm for clarity, I'm sticking to using the r, but r here is to be viewed as a function of u and v. It's just that we can't invert that r star function in a clean analytic expression, but that it's invertible. So there is our metric. It's now totally regular at r plus. So let's ask, what does it look like? So the way to figure out what it looks like, what our black hole looks like in these coordinates, is to try and think, well, what does r equals constant look like? What does t equals constant look like? What does r equals r plus look like? What does r equals 0 look like? Because there's no doubt that as r goes to 0, this exponential term is going to give you problems. So although it goes to, although it doesn't look like it does, the nonetheless our curvature still blows up at r equals 0. Actually, I'm just looking. Have I written that down right? I apologise. This should be. That's an r plus on the bottom. So I was looking at that and thinking, there's no problem with that at r equals 0. What's going on? But, sorry about this. For r plus divided by r. So now there's a problem at r equals 0. So my accuracy police missed that particular offence. So, right, let's look at r equals constant. So if I look at my u and v, you can see that if I multiply u and v, I get this e to the r star on r plus term in the exponential, which is purely a function of r. So if r is constant, u times v is constant. On the other hand, if I divide v by u, or u by v, all the r star terms cancel, and I'm left with an exponential of t. So if I want t equals constant, what I have to do is divide my u and v and set those to a constant. So now, what happens at R plus? Well, if I look at R equals R plus, this bracket here becomes 0. And therefore, what that means is that U times V is 0, because I got this term here by taking the combination UV. And finally, if I ask what happens as R goes to 0, so here I have to look at this thing here. If R goes to 0, this exponential becomes 1. And if R goes to 0, well, this is really R minus R plus over R plus. That goes to minus 1. So R equals 0 becomes UV equals R plus squared. So remember, there's this overall minus sign in front of U. So in terms of the UV coordinates, I've now got enough information to kind of start to build a picture of my black hole. So I'm ignoring theta and phi, obviously, at the moment. So we always draw null lines at 45 degrees, because intuitively we think of a null ray as somehow being t equals r, or t is some function of r. So we always draw null lines at 45 degrees. So this is my v, and this is my u. So I've drawn my coordinate lines u and v. And if I look at what is the condition that uv is 0, well, uv is 0 if u equals 0, which is this line here, and if v equals 0, which is this line here. So this whole sort of cross is r equals r plus. And I'll put this over here in inverted commas. But if I look here for, in terms of my normal asymptotic Schwarzschild coordinates, v is positive, u is negative. So this is our Schwarzschild space-time out here. So that's for normal t and r greater than r plus. So that's our physical black hole space-time. So the first thing that we kind of notice when we're drawing these coordinate lines is suddenly it looks like we've generated a new horizon. We have sort of two parts of the horizon. So that's kind of curious. So let's ask what these u and v, these r and t equals constant lines are. Well, out here, an r equals constant line is just like a hyperboloid. It's sort of a bent curve. And up here, though, this is now an r equals constant line. So remember, the u and v are null coordinates. So I've drawn them in increasing time. So what this now looks like is that this r coordinate inside here is now a time-like coordinate. Let's find another color. Time. So here we have now that t equals constant is basically u is proportional to v. So those are just straight lines coming out of the origin. It's not that distinguishable, is it? And so inside, for r less than r plus, notionally, t becomes a space-like coordinate. So where is r equals 0? We'll get the red chalk out for the singularity. Well, that's uv equals r plus squared. So that's just a particular hyperboloid. And there's two branches of it. So now I've drawn the essence of our Schwarzschild solution in these UV coordinates. Our space-time is just 1/4 of the UV plane, but we can analytically extend our space-time across the horizon, and in doing so, we see that the horizon now has a more complex structure. This, in this sort of top bit here, all light rays, all sort of information starting on the right-hand side crosses, if it's not going to escape out to the right, it crosses to the left and hits the singularity. So that means that that top portion is what we would call a black hole. It's the interior of the event horizon. Then we see that there's a mirror image at the bottom. And actually, we should have sort of expected that, because the Schwarzschild solution itself is time symmetric. If we send t to minus t, we get exactly the same geometry. And so formally, if we analytically continue for observers falling through the event horizon, that means that there's a formal image for past time, for t goes to minus infinity, that sometimes gets called the white hole. And then to the left, we simply have another Schwarzschild, so to speak. So that is our maximally extended Schwarzschild spacetime. It's what you get if you take the exact Schwarzschild metric and cross the event horizon. So does that mean we have to worry about white holes? Well, not really, because this is an exact, extremely precise solution. In reality, we don't have an exact vacuum, and in reality, our black holes have been formed by gravitational collapse, so they're not time symmetric. So in reality, we would have a slightly different structure, which, if you remind me, I'll sketch once I've finished talking about Penrose diagrams. So this is the mathematical structure of a black hole, but not necessarily representing the physical structure of one of our black holes in the universe. So let's go to Penrose diagrams. So these are a compact way of visually representing the causal structure of the black hole. And the idea is to take that picture where u and v extend out to infinity and kind of shrink it down, doing a sort of transformation by shrinking, mapping the v coordinate to a finite range and the u coordinate to a finite range so that it all fits onto a piece of paper. So how do we map an infinite range to a finite range? Well, we just use tans or tanh functions, because the tan takes a finite range to infinity. So So we take our exponential functions and take the arctangent of the exponential functions. This is now mapped u and v to a finite range. We ask again, what are the key sort of p's and q's that correspond to sort of useful values of u and v. So v is 0, corresponds to p is 0. V is r plus. So that's the arctan of 1. Corresponds to p as pi on 4. And v goes to infinity. Corresponds to p is pi on 2. And so similarly for u, and p goes to minus infinity is p goes to minus pi on 2. So, etc. Then we kind of use an addition formula to try and, what I'm after here is I'm after what happens to r equals 0 under this map. R equals 0 corresponds to uv as r plus squared. If uv is r plus squared, that right-hand side goes to infinity, and therefore tan p plus q is infinite. So that's another important value of u and v. So let's see what happens. Well, our v and u get shrunk onto the range pi by 2 or minus pi by 2. So this is the p coordinate, this is the q. So now we've shrunk our null directions, our whole real line onto a finite range. Then we say that the singularity is now mapped to p plus q is plus or minus pi on 2. So that's this horizontal line here and this horizontal line here. So what else? Well, if it's not constrained by this relation of the singularity, so for example, if q is negative, p can now run up to pi on 2. Enjoying colours here, so you're just going to have to put up with it. So p can run up to pi on 2, and q starts at minus pi on 2. And over here, q can run to pi on 2, and p starts at minus pi on 2. So this is now the full range of our space-time coordinates, where we've kind of shrunk them down or compactified onto a finite range. So this is our Penrose Carter diagram. So usually we just call it Penrose diagram. Poor Brandon Carter just gets dropped off most of the time. Reason why I'm not sure, it's probably lost in the mists of time. I should ask more. Okay. So what we've actually done here is encoded the causal structure. So let's look at what everything is. This is our singularity. This is the full event horizon. And all of this blue stuff out here is infinity. So this, and that is infinity in some sense, because it sort of represents the nether reaches of our original space-time. So we actually have labels for all of these things, not surprisingly. Let me put the labels on and then we can talk about them. So this one is I plus, I minus, I zero, scri plus, script I, scri minus, H plus, H minus. So H, obviously, stands for event horizon. And the plus or minus means future or past event horizons. So our future event horizon is the physical event horizon of the black hole. The past event horizon is this formal white hole horizon. The I plus is future time-like infinity. So if we think about waiting around in the Schwarzschild space-time until the clock runs out, this is where we would end up if we didn't, as a physical observer, so not a null observer, as a physical observer, this is where we would end up if we didn't fall inside the black hole. I minus is therefore its inverse, and I zero is space-like infinity. So space-like infinity is where you get if you go away from the black hole on a spatial geodesic. The other two bits of infinity are quite interesting. This is what happens in a asymptotically flat space-time. Scri plus or minus is future or past null infinity. So, as I say, in asymptotically flat space-time, there's a distinction between the infinity that a light ray sees that you set off now versus one a second later versus one a second later. All of those go to a different part of this compactified space-time. So when you're doing sort of formal sort of aspects of classical GR, these are the sort of labels or structures that you're interested in. So our formal definition of an event horizon, the physical one, so this is actually the formal definition of an event horizon. An event horizon is a boundary between things we can see and things we can't see, but how do we know what we can and can't see unless we wait forever? Okay? So that is the formal definition of an event horizon. It's a question.
So any observer following a time-like geodesic will eventually hit the
I plus.
But the scribe plus, where you hit depends on
when you leave.
Your initial conditions.
Yeah. So null rays hit scri plus at different times. So if we think about what's meaningful for us physically, there's actually quite a few interesting questions raised here. The first one of which is actually encoded in this. You know, the fact that, strictly speaking, we're saying that we don't know where the black hole is until the end of time, which is a bit useless, actually, if you want to be doing astrophysics with black holes, because you want to be doing it in the here and now, or maybe a billion years past, right, in terms of black hole mergers. So this raises an interesting question of what do we really mean by an event horizon when we are talking about numerical simulations of black hole mergers? So what we talk about, when you hear a numerical relativist talking about an event horizon, they mean something different, something much more sort of practical. And let's face it, this space-time is extremely idealized anyway. I've lost the thread you were talking about. Going to I plus Scry plus, right. So the other thing is, another useful physical notion is mass of isolated systems. So the first formal definition of mass of isolated systems was the ADM mass, which involved going to I0 and looking at the fall-off of the metric tensor and looking at, if you like, the 1 over r fall-off of the metric tensor and identifying that with the mass. So that's fine, that's totally okay. It's cool with Schwarzschild, but what happens if you have a time-dependent space-time? If you have a growing black hole, this is still I0, and the mass never changes. The mass measured out here is always the total mass in the space-time, which is the same. Whereas if you go along Scry plus, where you now have the possibility of things, of light escaping, and therefore carrying away some energy momentum, you can define a mass on Scry plus called the Bondi mass, which is now more realistic because it can change. So you kind of, this picture, whilst extremely idealized, kind of starts to raise the questions about how we define physically meaningful quantities.
So how does the mass along, which you define along Scry plus, change if only light can escape?
Because light carries momentum. I'm saying light because that's our, gravitational waves too, right? So anything that travels at the speed of light. So, but again, you raise this point about what do we mean by the mass of a black hole, which is something different from this formal classical GR mathematics, because we would like to be able to say, well, there's a black hole there, there's a black hole over there, and it's meaningful to us to say, well, that has mass m1, that has mass m2, but that doesn't actually fit in to the formal mathematics of GR. And people didn't really care for a while because, it was, I suppose it took a while to accept that there were real black holes out there, or to be confident that we'd seen a black hole. And also, until the last 20 or 15 years or so, the notion of the astrophysics of black holes merging, etc., was again somewhat out of reach of what we could calculate and what we could do. So I think this is an example where you've got a whole load of formalism that was developed in the 60s and 70s, sort of describing spacetimes and describing spacetime structure that at the time was much more in contact with how we were sort of talking about physical objects, whereas now I think it's become a bit more separated. Except, of course, some of the structure of Scry has kind of come back in the news, so to speak, in terms of thinking about soft hair and thinking about charges on Scry. So it's not totally useless. Let me just say what happens to Minkowski spacetime, which is with no mass. So here it's very easy. U is t minus r, v is t plus r, and r is greater than 0, so v is greater than u. So what that means is if I draw my u and v lines, I have to cut off half the space. I'm not really cutting it off, it's just that our radial coordinate just is the half of the real line. So this is Minkowski space, we've got our scri plus, our scri minus, r equals 0, no singularity. And we're suppressing the theta and phi directions. So that's Minkowski space-time. So what about other black hole space-times? How might I draw them? Well, the rule sort of is that every time we have an event horizon, we draw a cross, because that's sort of representing a null boundary. Or not just an event, any sort of horizon is a cross. So we kind of ask ourselves what happens. So let's take the de Sitter space-time. In our de Sitter space-time sort of has a causal horizon, so I might start by drawing the cross representing a horizon, but then I have to ask myself what happens beyond that. So here would be our static de Sitter, coordinates out here, but this would be the cosmological horizon, so that would be r equaled L, but then as we go to r equals 0, it sort of looks like Minkowski space-time near r equals 0, so that tells me I just draw the r equals 0 line. So this is what I've got here. And then, since I only kind of have one horizon, what I end up with for de Sitter is simply a square. So this is t equals infinity, some t equals minus infinity. This is either r equals 0, or if you're in global coordinates, remember I wrote down the global coordinates where de Sitter was like d tau squared minus sort of cosh squared times the metric on a unit 3 sphere. This would be like the south pole of the 3 sphere, and this would be like the north pole of the 3 sphere. So that's de Sitter space. And then Schwarzschild de Sitter, well, we kind of do the same thing again. Close to the black hole horizon, we have a Schwarzschild space. So here's our Schwarzschild horizon and singularity. Away from the black hole, we should have this sort of structure. So this is our black hole, and this is our cosmological horizon. Here's t equals infinity, cosmological time. But now, if I maximally analytically extend, I kind of just end up with the same copy. And so when I construct Schwarzschild de Sitter, I end up with a sort of infinite. I can keep analytically extending an infinite number of times. So that's sort of talking about causal structure. Now, what I'd like to do before finishing today is talk about something a little bit more realistic. And of course, the more realistic you get, the more messy it gets. So all astrophysical objects rotate, and so if a star collapses, you would expect the collapsed star, the black hole, to also rotate. Now, it's interesting that the Schwarzschild black hole was written down almost immediately after GR. Carl Schwarzschild kind of did his calculations in the trenches or at the front line in the First World War. So finding a spherically symmetric solution was pretty easy. Finding a rotating black hole took until 1963 or so, when Roy Kerr wrote down a solution for a rotating space-time. So it's actually quite fascinating. It took so long. So let's write it down. Now you see why I'm copying it down. I do not trust myself to remember this thing. There we go. So just as to put us on the side here, sigma is r squared plus a squared cos squared theta. Delta is r squared plus a squared minus 2gmr. A is j over m. So that's the Kerr in familiar sort of tr theta phi coordinates called Boyer-Lindquist coordinates. So this corresponds to what we might, it's very much like taking Schwarzschild and messing it around. But we can also, I think I was asked after the last lecture about these orthonormal frames. So here's just a slight rewriting of the Kerr metric, which now looks like an orthonormal frame. It's not unique. You can pair the t and phi off in whichever way you want. The usefulness of this particular choice of orthonormal frame is that you see here this delta function, which looks a bit like the Schwarzschild potential, that's now multiplying a time-like one form. So that's sort of what we're going to investigate is where the event horizon is for this space-time, and that orthonormal basis is suggestive that the event horizon is where delta goes to 0. So when delta is 0, this corresponds to r is r plus, there's two roots, obviously, because it's a quadratic. So the greater root, r plus, is at gm plus the square root of g squared m squared minus a squared. So notice that r plus is less than 2gm. So now let's think about something else. What happens to the norm of a time-like vector, d by dt, or what you think is a time-like vector? So our d by dt becomes 0, the norm becomes 0, when r is gm plus the square root of g squared m squared minus a squared cos squared theta. So notice that's always bigger than or equal to r plus. And in particular, if you look on the say on the equator, yeah, so on the equator that's actually 2gm. So that's a lot fatter than the constant radius sphere. So if the event horizon is delta equals 0, which is r plus, then it's impossible to remain at rest relative to an observer at infinity. So this now introduces something that is associated to a Kerr black hole, which is called the ergosphere. So the ergosphere is where you have to be moving with respect to infinity. So that's all true if delta equals 0 is the event horizon. So now we're going to actually I'm going to more or less argue that it is. So how would we know it's an event horizon? Well, the event horizon is the boundary between things that reach time-like infinity or null infinity and those that don't. So we have to explore geodesics. Now, geodesics in Kerr are a lot more complicated and interesting than geodesics in Schwarzschild. A geodesic, once it has angular momentum, it obviously behaves differently if it co-rotates with the black hole or counter-rotates. So I don't know if you'll be doing that in the strong gravity course, but it's really neat to actually look at images of the sort of gases falling into a black hole. So what do you see when you look at a black hole? Because, you often see these wonderful artists' impression of this nice little round black sphere sort of out there with a nice tidy accretion disk going round it. But if you've seen Interstellar, then you know the accretion disk doesn't necessarily look quite that neat. It's all distorted. And furthermore, if you start actually looking at the simulations that the guys here and elsewhere, of course, have been doing for imaging of the Event Horizon Telescope, you'll see that, the images are actually quite messy. And if you get a transient event like something being sucked into the black hole where there's a sudden bright spot, that's not this nice sort of swan dive into the black hole. It's sort of, you actually see behind the black hole. So it's quite a messy splotch that's time dependent. But this is kind of, this is sort of some of the cool stuff anyway about looking at black holes. So let's explore geodesics, but I'm going to do it because I want to do it on the blackboard. I want to do it analytically. I'm going to look at equatorial geodesics because then there's a lot of simplifications, and it still highlights some of the differences that you get when you're looking at the Kerr black hole compared to Schwarzschild. So on the equator, this discrepancy between delta equals 0 and GTT equals 0 is at its greatest. So any effects of the geodesic kind of being dragged around by the black hole will be maximized. So first thing is, when we're doing geodesics, we want to make things as simple as possible, so we look for constants or conserved quantities. So here, we wheel out of our armory the killing vector. If we have a killing vector, then if we contract it with the tangent vector to a geodesic, it turns out that we end up with a conserved quantity. So let's just see this. So along the geodesic, d by dt, so this is your proper time, is just the tangent vector dotted with grad. So I take it in turns. I do x dot mu, acting on the killing vector. Sorry, my indices have...
So now, everybody, please stop paying attention because that's your homework.
Seriously?
Yeah. No, please go.
I'm giving you a gift. Or maybe I'll leave the indices all wrong so you can correct them. Okay, whichever way. This thing's a geodesic. You see, David likes his symmetries and conserved tensors and vectors. So that's 0 because it's a geodesic. This is 0 because the killing vector has a symmetric covariant derivative, which we didn't prove. So maybe you can do that for your homework. Right, so this tells us that this thing is a conserved quantity. So Kerr has two killing vectors. It's no longer got the SO3 algebra because it's rotating. So it has two easy killing vectors, d by dt and d by d phi. And David might try and persuade you there are other conserved things, which is fine. So let's have a look at d by dt. So this corresponds to a conserved energy. Which is our downstairs components of k mu are gt mu. And so that is if at the equator, so I'll leave you to verify these expressions as exercises, since I've given you a freebie on your homework. So that's your energy now in Kerr. And then for k phi, which is d by d phi, gives you an angular momentum conserved quantity. These are fairly easy exercises, by the way. So you see now, whereas before the energy would just be directly proportional to t dot, it's now got a mixed sort of aspect to it of t dots and phi dots. But now if I define, sort of group these together, into just, I'm sort of splitting my space-time into a sort of TR piece and a theta R piece and a T phi piece. So here, what I'm aiming towards is looking at the geodesic equation as the first integral, where you kind of say, well, the length of the tangent vector is 1 for a time-like observer, or 0 for a null observer. So this So what you see is that if this were just Schwarzschild, you would just have a sort of E squared, R squared, and then the H squared terms. But here, you see you've still got the sort of H squared and E squared pieces, but the 2GM on R, now if H is plus or minus, i.e. co-rotating or counter-rotating, you see this term has a different magnitude. So our geodesic equation on the equator is P squared plus GRR dot squared is eta, which is 1 if we're time-like, and 0 for null geodesics. And so, sort of characteristically, if we want to just qualitatively look at the behavior of geodesics, we kind of write things as sort of particle motion in a potential well. And so this equation has the form R dot squared plus V effective of R equals 0. So it's like a way of getting qualitative behavior of geodesics. So this V effective is eta times delta over sigma minus P squared delta over sigma. And so we see the sort of characteristic parts of the effective potential. We've got a Newtonian potential of 1 on R. We've got a sort of centrifugal piece, which is H squared on R squared. And finally, we've got this GR piece, which now sort of has different sizes depending on whether you're co-rotating or counter-rotating. So when you sketch this potential, you've kind of got the negative Newtonian part. You then come into a centrifugal part, and then you finally come down to the GR piece. So this is your GR dominant, this is your centrifugal, and this is the Newtonian part. And so qualitatively, when you look at what geodesics are like, you've got stable orbits, circular orbits down here. These are elliptical orbits, where R sort of rolls between one and the other. This is circular orbit. This is unstable circular orbit. And then you have geodesics that come in and get captured. Those are sort of the things that get sucked in. And you have scattering geodesics that come in but come out again. So those are things that are deflected by the black hole. So that diagram qualitatively represents all of the possibilities of geodesics without actually solving the geodesic equation. So I think even though we started late, I probably should stop now, and we'll just kind of finish off a discussion of black holes next time. I think I was having too much fun earlier. That was why I slowed down.